Alright, so we're ready to take a look at the first example for a quadratic function that's in our notes. We have f of x is equal to x squared plus 4x minus 5. So what I want to do is I want us to find the vertex, the axis of symmetry, the intercepts, and the graph, and the domain and range. Let's find everything. Okay. So, let's go and do this. Let's list out what we need. We need to find the vertex, the axis of symmetry. We want to find any X-intercepts. We want to find the Y-intercept. And let's go ahead and talk about what is the domain and what is the range. And once we're done with all of this, then we'll go to some graph paper and graph it all. Alright, now if you go back to what we had in the last video, this is in general form, which means it's easier to find the intercepts as opposed to some of the other qualities about this. Now there is a gimme here. One of the gimmes is the domain. For a quadratic function, the domain is supposed to be all real numbers. So we can go ahead and say from negative infinity to infinity. Because we don't have any of those weird things that are going to limit our domain. We don't have fractions, we don't have radicals. It's a polynomial. And in a polynomial function, the domain is all real numbers. The range, we're going to have to wait a little bit till we get to that. Now, one of the things to understand is that since this is a positive for a lead coefficient, my expectation is to have a parabola that opens up. And since it opens up, that tells me that my range is going to be from whatever this y value is, going up to infinity. So we at least should be thinking about that, thinking about the shape. That way it's going to help us and guide us to get the range and some of these other values. The y-intercept is another nice, easy one to get. Because we know for every y-intercept, x is equal to 0. You can only ever have one y-intercept for a function. Since the domain is all real numbers, we know that it must include 0, so we just need to plug it in. But that's simple enough, right? 0 squared, and that's gone. 4 times 0 is gone, and we're left with a negative 5. It's as easy as that. We don't need to make it more difficult. The x-intercepts. What we said about the x-intercepts is that we need to take this equation and set it equal to 0. So, off to the side, let's just write this. So for the x-intercepts, we're going to solve. We're going to solve the equation x squared plus 4x minus 5 equals 0. All right, it's a quadratic equation. We know how to solve these. Let's go through our progression. Can I use the square root property? No, because I have two instances of the variable. Second thing I try, can this guy factor? Well, yeah, we can find factors of 5 that subtract to 4. So this will factor as x plus 5 times x minus 1. And then from here, we can solve this using the zero factor theorem. X equals negative 5, or x equals positive 1. Since these are real solutions, they directly correspond to x-intercepts. Each one gives you an x-intercept, because think about what the parabola looks like. The quadratic function does this, right? He dips down like that. So he's going to dip down, he's going to hit once, he's going to come down, he's going to hit again as it goes back up. Now they don't have to do that. We've talked about how it could be this, where it just kind of totally misses as it bounces, or it could come down and just tap it and go away. This guy's going to go through once, here at the ordered pair negative 5, 0, and then again at the ordered pair 1, 0. Each of those real solutions corresponds to an x-intercept. All right, now we have to find the vertex. All right. So it's vertex time. Make sure you remember the vertex formula, which says negative b over 2a is the x value. And once you have that x value, plug it into your function to find the corresponding y value. Okay? So let's work that out. If I take negative b over 2a, So that's going to give me negative. B is 4, just like we would have picked off B and A for the quadratic formula, right? So over 2 times A positive 1. Working this out, that's negative 4 over 2, which gives me negative 2. That means that the x value for my vertex is negative 2. Now right there, we can go ahead and start filling in some things. So my vertex is going to be the ordered pair negative 2, comma, something. I'm going to figure out what that is in a moment. But since we know that x equals negative 2, that tells me that the axis of symmetry, that line about which we can copy one side to the other, is going to be the equation x equals negative 2. So whatever the x value is for the vertex, that is how you write your axis of symmetry. And you do need to write x equals, okay? If you don't have x equals, then you don't really have a line. So the line of symmetry is a line, right? And since it's a vertical line, it takes on the form x equals. So what does x equal here? For the vertex, x equals negative 2, and that vertical line goes right through that point, right through that vertex. So now we have to evaluate f of negative 2. Okay, so let's do that here. F of negative 2 is going to be, let's see, negative 2 squared plus 4 times negative 2 minus 5. Working this out, that's positive 4 minus 8 minus 5. All right. So 4 minus 8 is negative 4, minus 5 is negative 9. And that is the coordinate that completes our vertex. Just like that. All right, so we have all this key information. We're going to come back and answer the range here in just a second. Let's just go ahead and jump over to the graph and see what this guy looks like. All right. So let's do this. Our key information, let's go ahead and plot that. We have a y-intercept of 0, negative 5. So there's that guy. We have x-intercepts at negative 5, 0. Okay, and 1, 0. All right. We have an axis of symmetry of x equals negative 2. So I'm going to mark that guy here in green. Negative 2. All right, so here we go. Remember, this is a line of symmetry. All right, and we have a vertex at negative 2, negative 9. So negative 2, see how that matches up, down here at negative 9. Okay? Now, let's see if there are other points that we can add here. Since you have a line of symmetry, notice how this point is 2 units to the right of the line of symmetry. So if we go 2 units to the left, you should get another point for the graph. Another thing to consider is this. Your quadratic function has a lead coefficient of 1, which means it's going to have the same shape as the parent function. It's just now starting here at the vertex of negative 2, negative 9, which means if you kind of dash out like a new x-axis down here, just like we've done before, you make that 0, 1, 2, 3, and so on. Okay, 1 squared is going to be up here at 1, 2 squared is up 4 units, 1, 2, 3, 4. See, that makes sense. It lines up with the y-intercept we already have. 3 squared is 9, which is right here. 4 squared is 16, so this is 9. 10, 11, 12, 13, 14, 15, 16 is right here. And now we can copy these points on the other side of your line of symmetry. So that's up 1, 4, 9, 16. And now we just need to connect the dots, making a nice, smooth, parabolic curve. Please make sure that you remember on the ends, this guy's still going up and up and up as it moves out. Do not change the way that this is curving. This is still kind of curving up. Don't turn outwards like that. Also, do not go vertical. Parabolas are never vertical because if they were, then they would fail the vertical line test. Okay. Now I want to show you something else with this one. Let's go ahead and label this before I move away. Okay. There is another way for us to identify the vertex without using negative b over 2a. And here's what we can do. We can complete the square. So I'm going to come back over here so we actually have enough room to do this. I'm going to take my original function, alright, so we have x squared plus 4x minus 5. And I'm going to complete the square in order to convert this from general form into the vertex form. And the way we do that is that we have to kind of regroup things. I'm going to take these two terms right here, and I'm going to put them in a set of parentheses. However, I want to leave a huge gap here that I'm going to need to fill in. Okay? So here's how completing the square works when you only have one side of an equation to work with. See, when we solved equations by completing the square in the past, we would change something on one side and then add the same thing on the other side. We can't do that here because we have a function. Here's what we're going to do. We're going to go ahead and work like we're completing the square, like this. Now, when we would complete the square before, we would take this number right here, as long as this is a 1, we would do half of 4. So half of 4 is 2, and that goes in here. And then 2 squared is what goes in to fill in the gap, and you would say plus 4, right? Divide by 2 and square it. But I just added 4 on one side of my function, so I've totally changed the problem. Unless I take away 4. So if I add 4 and I take away 4, I've actually added 0 and I haven't changed anything. Okay? But here's what I'm going to do. I'm going to take these first 3 pieces right here to give me a square. And it's this minus 4 that I'm not using. Now, it's understood to have a coefficient of 1 right here. So when you have this negative 4, you're going to bring him out by multiplying him times 1. So he comes out as negative 4, along with the negative 5 that's already out here. And now once I clean things up, we have x plus 2 quantity squared minus 9. And you can see from here, just like we've talked about before, how this guy means that you go the opposite horizontally. So you would go left 2. And this guy means that you would go down 9 units. Well, if you go left 2 and down 9, well, you get this guy, right? So it's the same picture. We just rearranged it so we could see it in a slightly different way. Now let's come back up here and answer the question about our range. Normally your range is going to be from 0 to infinity, but we brought everything down by 9 units, so the range is now starting down here at negative 9 with a bracket, going all the way up to infinity. Okay? Let's take a quick break and come back for another example.